This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. I hope I'm clearly recording because the mobile mic is not working. Before I start, a couple of things. Your workshop report marks are being posted. If you see a 0, don't panic, because one of the demonstrators told me he's still marking, and he uploaded where the system automatically converted the blanks to 0. So that doesn't mean anything. So you will get, if you have submitted something, you should not get a 0. There should be at least a 1. All right. So I told the demonstrators don't give 0, right? So that's even partially don't give 0. So if someone has shown the effort, he should get at least a 1 out of it. So if you see 0, that's a placeholder. If it is not getting corrected, contact your demonstrator and it will be corrected soon. All right. And sorry for the delay in marking. The demonstrators know of the delay, and the next reports will be marked much quicker. And then they will be marked you will get your marks well before the final exam, which is already scheduled, right? So has it been released, the schedule, which date it is going to be? Not yet? Well, you will hear it soon, officially. Yeah, it's not out yet. Good, that's one thing. The other thing is, I got feedback from Student Staff Liaison Committee, SSLC. Some students went there and gave some feedback about how the subject is going. Actually, beyond that, I'm very happy with this cohort in terms of interactions. Many students come to me, ask questions, give feedback. Some people show up to the consultation hour. And it's very useful because it allows me to improve things for you, even now that things will be even better next year, but even now things are improved. There were a couple of things raised during that feedback session, and I would like to quickly address it because we discussed this already. Some people said, oh, there was a mismatch between math background expectations and what we already know. So that is something I realized at the 1 month mark myself, obviously. And then we tried to address it, adding a bit more clarification to notations and so on. I see it as a work in progress. And before the final exam, I may even put some notational clues and so on, so that when you do the self-study, you can catch up. I already say that I'm not doing math for math's sake. I'm only doing enough math so that you can comfortably say I have completed the proper machine learning, deep learning, machine learning system optimization subject. And there is a minimum. If you fall below this minimum, we do this service to you and we do this service to the institution, right? This is not a mediocre university. It's in the top 100. Which I believe is a deserved top 100 university in the world. So we need to hit some standard. But if you don't know, if you had gaps in your knowledge, I gave you a lot of pointers. We discussed it, and it is your last chance to fill it. Because when you go to work, you cannot go to your boss and say, "Oh, give me 3 months. I need to study this stuff." Right? It doesn't work that way. So therefore, it is good that you also see the gaps and finish it. I will do it in a gentler way next year, of course, but. There is also some minimum to hit. Similarly, there were some complaints about the workshops being too short, but I already addressed this. First 2 workshops were 3 week long, remember? And the last 2 ones I'm consciously making. This one, for example, I made it consciously shorter, and many people told me, yes, it is shorter, so it should fit to 2 weeks. The last one, I will be also very conscious about the length, so it will be a very short one too. Because next year, I'm going to do only 3 workshops. Make it short, condense things and 3 weeks each. But you are not winning or losing anything because when I merge them, I will merge the similar things. So that's the same story. And many people said, oh, there is a lot to learn in Python, a lot of libraries to learn. Just like the math, it is an important skill that you should have. You should be, as engineers in 21st century, you should be able to use software packages following the manuals with some help from the demonstrators. If you don't have that skill, this is, again, the best time to get that skill. Again, in the job, you go and, you want to, if I were hiring something and the guy asks me or the person asks me every other day, what is this, what is that, I cannot find the manual, I cannot find it in the manual, that person will be fired the next week. So it is again a skill that you should achieve. And the software tools I'm using are again very, very cutting edge, normal things that everybody uses. And then another last feedback was, I don't give enough examples. This is not true. I give either example code or you should bother clicking. I give links to some online sources where people solve the same problem. I gave away the answer actually in the first workshop. It was one click away. So then people told me, oh, I didn't click it. Then I'm asking, why didn't you click it? Like, what can I do? The answer was there. In another one, I included the answer by mistake. It was there, just the answer was there. So you just needed to change the numbers. So the things are, is a progress, but like it's a give and take. I will meet you in the middle in terms of exams and knowledge required, but you should also meet me in the middle, so that we achieve the good quality and you learn nice things, so that you can comfortably write it to your resume, and then when you go out, it makes a difference hopefully for you, right? So it's something good to learn. I think everybody agrees because it's an elective. I mean, it's not a mandatory subject. So that's my feedback on the feedback. And then we continue with the nice topic of neural networks. So we have been discussing what a feed-forward neural networks. It's one type of, and the most common type of neural network. And then we talked about the architecture, a little bit of the history. Then we said, how do we train these neural networks? And then during the training discussion, you start the training discussion from the objective functions. Because, as I said, the training is done through an optimization process, and to optimize something, first you need an objective function to optimize. We know what the decision variables are. The decision variables are the parameters of the weights of the neural network. I want to find them. And then I mentioned a couple of different objective functions that come from the maximum likelihood for classification and regression, and how things tie to each other. So today we will continue a little bit on that. And I was talking about the condition, the KL divergence, maximum likelihood high, cross entropy, and the cross entropy loss is the most commonly used, or variance of it is most commonly used for today for classification. And then the mean square error, again, which ties, as I showed, to maximum likelihood, is also very commonly used for regression if you use the neural network for regression purposes. So let's look at I also included simple questions. And speaking of questions, I will kind of give a study guide for the final exam, which questions you should focus on. Because there are some questions I included only for informative purposes, and some of them are kind of, you should be able to do this type of thing. It's not clearly marked. I will either mark it and upload accordingly, or I will also probably look at these set of questions from these modules. So these are the ones that you should study. Together with the end of chapter, you should know this, that type of thing. I think it will give you a view what to expect. The final will not be different from the mid-semester test in terms of style and content, and then the simplicity, it's even simpler, maybe. But then I always get it wrong, so I shouldn't promise. It's very hard to, do it, even if it's wrong, it's not a problem. If it's too difficult, then we give more partial credit, and vice versa. If it's too easy, then we don't give that much partial credit. So it comes to the same thing. All right, so question 2. So let's do a couple of questions, actually, that goes to the matter, and then instead of saying it at a high level. Oh, also someone said, why don't you show during the lecture some programming as a preparation for the workshop? Yeah, that's not the right environment. Also, it's a waste if I do that, because these lectures, I see them as giving you the background and the knowledge, theoretical knowledge, and then they are nicely complemented by the workshops. They serve different complementary purposes. So in that sense, we do a bit more theory in the lectures, and we do purely practical stuff in the workshops. All right, so derivative of the cross entropy function with respect to the activation function for an output unit having a sigmoid activation function. So we have that, and then we want to find the derivative. So this is our loss function. What we have here is that this is our objective function. Then, you know, if we want to optimize this, obviously we need the derivatives, right? It's all about taking derivatives, to be honest, when it comes to training these neural networks, at least as of today. You know, people may discover different things in the future. So if we take the derivative, and then with respect to what? First we need to, it says to take the derivative with respect to the activation function. So we take it with respect to the A, and then A is tied to W's as well. So, you know, as you can imagine, there is the chain rule. So we are doing part of that chain rule right now. If I take the del E, maybe not red, so this is the cross entropy error or loss function, so it's the same thing, just to make it clear. So if I take the derivative with respect to A, right, so we have then, well, y is actually function of A, that's how the dependence is. Tn is a constant. In this case, y is the output, Tn is the label. So, and this is the one that we discussed in the slides, over the data points, summed over the data points. It's a sigmoid, so sigma A is this. We know that as well. So if I take the derivative with respect to A, why not do it? Let's do it. So we have then minus Tn is there, but then A appears as part of a y of A. So this is like a y of A, right? Then log y of A with respect to A is basically 1 over y n times the derivative of y with respect to A. That would be then del y del A, right? And similarly, 1 minus Tn, I get then 1 over 1 minus yn del y over del A. And then let's take it with respect to specific 1 with respect to an. All right. So because if you take with respect to the specific 1, then all the others are irrelevant. So the sum, only the nth one or the kth one. So if you can, you know, the specific one out of those whole sum is the one that we are taking with respect to the partial derivative. So we have, we know that del sigma, you know, sigmoid's derivative with respect to its argument is itself, and this is very handy when you do computation, obviously, itself multiplied with 1 minus sigma. Therefore, when we take the derivative of del y del an, what we get is y. Actually, we can write it like this, right? So we can write this. So we have yn here. Let me be more precise here. So then it would be then yn 1 minus yn. So this is background knowledge. We know this, right? Therefore, when we put this in, we get then simply del e del an. We get minus Tn. And if we combine with the terms, that gets yn 1 minus yn divided by yn plus 1 minus. This is actually a very, very simple question, but no harm in doing a bit of practice. Divided by 1 minus yn. Right? So we got the cancellations, and then we can rearrange the terms. Things cancel out. We got the yn minus Tn. So that's quite reasonable, and that's what we wanted to show, you know, as expected. So the derivative with respect to the activation function is actually the error, the delta between the output and the what it should be, the label. So that difference gives me the derivative. When I hit the right one, the derivative will be 0. So that's kind of also has an intuitive meaning to it. All right. Any questions? Yeah, this is something you should be able to do, obviously, you know, as an exam level. And as part of the process, training process, I will just come to, it will make a bit more sense. This is a piece of the puzzle that will become immediately clear in a few slides when I discuss the backpropagation. Before doing that, though, I want to give a bit more kind of a few comments on the cost function and the gradient. So so what we want is actually, we want a large gradient and predictable enough for efficiency of learning algorithms, because gradient, if we use a gradient descent type of algorithm, the gradient determines the step size, and otherwise if the gradient is small, it takes forever to converge. But you have experienced this already in the workshop 1. The same thing happens when you train for the neural network with a gradient algorithm. And you will see that all of the, even the most sophisticated ones, go back to the gradient idea. The functions that saturate become very flat undermine this, because they make the gradient very small way before you reach the solution. So if it's flat, if it's a flat basin of a ball, then you hit it far from, you hit the flat area far from the solution, then your gradient will be small, and you'll have to automatically take small steps, which will mean it will take forever to train it, and that's not good. Of course, we want to train quickly if possible. So therefore, we want to choose the activation functions that that don't become that flat. The ReLU actually in the non-zero region is y equals x, so that is not flat at all. So that kind of is very nice in terms of gradient, right? So the activation function, it still has the nonlinearity of zeroing out the negative values, but ReLU function is been one of the reasons why it's been popular is unlike tangent hip hyperbolic, it doesn't have these flat regions. It doesn't squish things like that. It either deletes or you stay as identity. Another thing is negative log likelihood also helps avoiding this problem for many models because of this logarithm, when you take the derivative of the logarithm thing. And then, whereas mean square error, mean absolute error may lead to poor results, especially for classification. So classification, people like the cross entropy cost function is a very popular tool. So maybe I should make a note here in terms of for classification purposes. Problems is very popular, for classification. So I think maybe this is not clear here, because we still use the mean square error for regression type of problems anyway. But cross entropy is very popular for classification purposes. So that's something that we can also put it, so that when you go back, you can read it. So there is a lot of, I was talking about the neural network zoo to show the diversity of the possible types of neural networks. There's also a lot of diversity in terms of the activation functions. So this is just a small set, but you can, everybody came up with their own different activation function, and if it works well, then it gets accepted. So we have the rectifier linear unit. That's for the hidden units, hidden layers. ReLU is the most popular. Sigmoidal is well known. Hyperbolic tangent is also was very popular in the earlier days. They relate to each other closely anyway. These days, not many people use it for intermediate layers, hidden layers. Hidden layers people use mostly ReLU. Then there are variants of ReLU, like leaky layer ReLU, where you don't zero out, but you put a small function going like this. Some other variant, then there's 10H and sigmoid. They look like these soft step functions, right? Remember, the first thing was, back then in perceptron, it was a step function. So these actually, the sigmoid is like a step function where you can take the derivative. That was the whole idea. The softmax is like the derivative version of max that you can take derivatives. For the output units, for regression, usually linear unit is used. Binary classification, sigmoid is used, because just like logistic regression, sigmoid gives you 0, 1. And then for multi-class softmax is also, we use the softmax for the multi-class classification. So these are the ones for the popular choices for the output units. You see, this is kind of a bit practical as well. As I say, there are some intuitive reasons for choosing them, but these are all design choices for creating the architecture, and there isn't a deep theory for doing the architecture. Most of the time, people choose the architectures by trial and error and experience. Any questions? You started doing this also in the workshop, right? I asked you to I gave you one version of an architecture and say, play with the architecture, add more layers, increase the numbers, try different activation functions. I was hoping that you would do that for this workshop, which is ongoing. Or maybe it isn't started for some of you, but you still have the manuals. Any questions? No? All right. Backpropagation. Now the most famous training algorithm, backpropagation, for the neural networks. Everybody knows about this. So we should also go through it. So this is essentially gradient optimization, as I mentioned, for training the weights, right? So just to repeat, in training the neural networks, find the weights by solving this optimization problem. As we discussed, J can be, there are a lot of choices for this cost function to minimize, and it may come from mean square error or maximum likelihood or cross entropy. So the things are interesting there in terms of the choices and their relationships. But the important thing to notice is usually this is a non-convex optimization problem. So we will use the convex optimization methods, but they will give us only local minimum, right? In the non-convex case. So we need to be very careful about that. And then you choose different starting. There are methods to handle this to get a good result, but you cannot guarantee the minimum, right? Because when the problem is non-convex, getting guarantee is very difficult or impossible for complicated functions. Still, as I said, we use, everyone uses the iterative gradient algorithms like this. Most of the time, these are very high dimensional problems. Therefore, Newton type methods are out of the window because your Newton, the Hessian matrix would be huge to invert. Even the approximate Hessians would be very, very large. So people go with more straightforward gradient descent variants for this. So, and this part is, as we covered in the, nothing new here in terms of the gradient method. I wanted to, I don't know why I put this here, but maybe I saw some confusion somewhere. Learning is not optimization. Optimization is used for learning, right? Yeah, there is a contextual difference, I guess. Because once you bring the learning to an optimization formulation, yes, you're using optimization for learning, but what you're trying to do is more than just optimization. So you're trying to take the data and do something, and it's a bit of a superset. Okay, so now let's do it. This is I'm following Bishop. To be honest, I looked at the deep learning book and the derivation of backpropagation in deep learning book. I found it extremely confusing. I don't know why they confused it like that. When you go to Bishop, actually it's very clean. And then what I felt is deep learning book took Bishop's analysis and made it just messier. And it seemed like a nightmare to me, so I went back to the original source, and I'm kind of happy with it. The backpropagation algorithm for a general network with arbitrary feed-forward topology, arbitrary differentiable nonlinear activation functions, and broad classes of error functions. So where the error functions are summed up over the data points. So this means this covers all the ground. You know, it's not the it's more honest to say, you know, the limitations of the analysis, but this is broad enough. So for this, we need to focus. The focus is on finding the gradient, because once we find the gradient, what we do is this, right? So we do a gradient descent. So the whole story is about, can we find the gradient with respect to the individual weights by taking error from the output to the backwards. So this goes back to actually, I hope I'm not mixing up things, but this goes back to the original AI credit assignment problem. You know, what do you do to influence the output? When you take the derivative of the error with respect to your parameter, that is almost like a relationship between how you change the weight and how that affects the error, right? So that's like you build that connection in a cascaded way. That's why you do this, you know, product derivative rule, right? Okay, and then as I said, the gradient is used for that. Now, as a motivating example, and then we already did one example just a second ago as well, but as a motivating example, let's say we do a mean square error for a linear model where we don't even map x to any phi of x. It's a purely linear model, linear in x. Then if we take the gradient with respect to the w, obviously this is the product rule, then you get this, right? So you take the derivative, then 2 times this, 2 cancels out itself for the En. We do it for the nth one, and then we take with respect to Wij, which comes from one of them, so it comes from one of the elements. Therefore, the other elements are not applicable. That one element, you have the function times the derivative of y with respect to x, because this is constant. Y with respect to x is only the y with respect to w is only x, so then x and I, that specific input to that specific element is the product. So this is just the product rule. But then there is this general form: gradient is error times input. So now we need to generalize this. And surprisingly, you can actually put everything to one slide. Maybe I should subdivide this slide, but this is really good to have a great overview. So the picture to have in mind is this. Maybe that picture needs to be here again. So this is the picture. Yeah, I should add again maybe. This is the picture, right? So we have inputs, hidden layer. There's this linear mapping, activation function, linear mapping, activation function at the output. So we are doing one layer only, because the multiple layers, then the product rule, you repeatedly apply. Right, maybe I should put that slide, picture slide here before this one. But keep it in mind. So in general, a unit J computes Zj, which is the activation of the function of the A, activation input, and A is the previous node's output, outputs, doing the linear multiplication with the matrix, and then that output goes through the activation function. So at every node, this is what happens, right? Every node of the neural network, regardless of other than input nodes, this is what happens, right? Then the chain rule, the derivative with respect to error is En with respect to W is En with respect to A, and A with respect to W. All right, that's the basic chain rule that we know. So here the good trick is you define this delta J to del En del Aj. Therefore, once we define this, then this becomes, notice that this derivative with respect to Aj, now it has become delta J, good. And then del Aj, del this is basically Zi, right? When you see here, you see then when I take the derivative of this with respect to the Wji, then I get the Zi here directly. Okay, so now this expression was the beginning expression. I applied the product rule once, then I get this expression, okay? Nothing mysterious going on. Next, for a hidden unit J, then now we need to look at this, because Zi is already we have. So this is what I was saying in a previous slide. The gradient is error times the input. The partial in the chain rule, the same thing, error times input. So now the input is that, the error is that. So now we do this. This is what I defined, right? And if I write it down, this is actually in terms of again I take the with respect to, I again use the chain rule with respect to the other A's that come into the picture, and then del AK, del Aj, right? So this is done over the sum. This is just the product, again, chain rule here. Just applied the chain rule. And if I substitute the definitions, then this definition is this. So this is now definition of del En to del Ak. Then this becomes not del J, but del K, right? So this comes here as del K. And then del Ak to del Aj, that will give me, right, through these 2 points, it will give me H prime, because A with respect to A, this A is W times Z, but Z is connected to the other Aj, the other AK. No, AK is sum of W Ki Zi, then Zi will be then H of AK, Aj, right? So each of them will be coming here through this derivative. So the derivative will be then the activation function's derivative, and then times the w's that come here. And then you take the sum is the same here. So for each element, we do this. So we take these two come together to create that derivative. And then because this is not summed over the k, this can be put outside the sum. This was here, so we have all the elements. So we get this, and then what we do is we do this in a recursive way, back propagate from the output, because the error is at the output. It needs to come back all the way to the previous layers. So there is del 1 to del k. Each of them goes back to the previous element, which has the input, which is its input and output, and then this goes back. The error propagates, delta propagates back. So you need to follow all the links here. So so this is not visualized, but this is algebraic version of this. You can also check Bishop for that. I have a visual thing too. But if you look at it as an algorithm, apply input vector to the network and forward propagate the activations of all hidden and input units. Essentially write that big function that gives you the output given the input. Then evaluate all the errors for all the output units. Then back propagate all the deltas to find the deltas for each hidden unit. So this is what we did here. Find the deltas for each hidden unit, j. And then use this. Essentially, the derivative with respect to the weight is just that specific error and input to that unit to calculate the error derivatives, right? So this will be for a single point. Then for multiple points, you sum them up to get the for multiple data points, you sum them up to get the total error. So so that is the dry kind of version and then the algebraic version. Again, I refer to the appropriate chapter that I mentioned in the beginning of Bishop if you want to go through it. But even better, just the other day while surfing the web, I found an excellent demonstration animation that I really want to show to you. I hope it opens up. So this is with thanks to Google, right? So I think it's one of their developer things. So backpropagation algorithm. So now this is a visualization of what I've been talking about. Please scroll down. Let's scroll down. So we have a neural network. You see there is an input, 2 hidden layers, another 2 hidden layers, and output. Okay. So this is kind of a not a single hidden layer, but 2 hidden layer network. You see the weights that are multiplying, right? Okay. These are the weights of the input weights, the output weights. Everyone clear? So then we go down. Now we need to put the activation function. So once the weights sum up, that becomes an input to this unit. Every unit goes through its own activation function f, and you get an output y, right? So this is also doing that, and then that output is used, multiplied with omega again, and then this is the output activation unit. The input unit doesn't have anything, so x input is y1. So there's nothing going on here. Then it goes through. So let's say it mentions sigmoid function, but ReLU is also commonly used. Now the error function. What is error function? The target and my output, the difference will give me the error, right? And then I put the error, and then loss function will have that error, representation of that error. Then I take the derivative of that loss function with respect to these w's, weights. That's what we have said. You can use, for example, mean square error or square error. All right. Now the forward propagation that I mentioned, you take the inputs and the target, y1 is x input, and then you sum them up to get the xj, right? And then the other one, and then you pass it through the activation. You do the same thing here. Now this layer is done. You see, that's why like it's a layered feed forward. There's nothing going on other than just layer by layer forward. Then the same thing is happening here. These 2 outputs are combined to get the input x. Then x, this was our a in our notation. Then it goes through the activation, which was h instead of f. So you do this here as well, and then go through the other one, right? And then now this layer is done. So we go to the output layer and the output. Right? So you write these equations because they help when you take the derivative. And then now when we take the derivative, we talked about it. You do a gradient algorithm. We need to find this derivative here, right? And then we continue. Additional derivatives are needed. We need to find all the intermediate derivatives because of the chain rule, right? The sum and product, the chain rule, the classic chain rule from the calculus, nothing different. And then the back propagation starts from here. So you get this derivative with respect to output. This is the y output minus y target, right? Then you take the derivative. Then here it is written in the, I usually write it the other way, but dE dx is dE dy and dy dx. So they wrote it, I don't know why, reverse. But then this is the initial chain rule. So you need to take with respect to the activation function, right? Derivative with respect to the activation function, and then with respect to y. Here, because of the sigmoid, you get sigma times 1 minus sigma here, right? And then we go to the back propagation now. Like this one is this with respect to xj, del xj, del wij, but then this is yi, and then del e del xj, and then you go further here as a sum, and then the sum here, there is that graph that you need to think about because of the chain rule here, and then it continues like this essentially. You go through the pieces, all of the pieces, and then that's the end. Right? Somebody did beautiful visualization of the whole process. That's I summarized in one slide there, like what's happening. The core of it is in the slide. Right? You need to kind of spend maybe half an hour to 1 hour to see it yourself, but then we are doing nothing but the chain rule. But long and short of it is that. So there's nothing else here. All right. So let's do a question for a single hidden layer one. I think this is a good question. It just brings a small twist and also allows us to do it by ourselves a little bit. No, actually, no, the other one is that. So this is an intermediate question. We play with the, we kind of get to see an interesting property here, and then the other question is where we take the derivative with respect to the errors, weights, and then do kind of a little bit of backward propagation here. All right, so let's do these. I still have time, right? Yeah, I have time for at least one question. So question 3. So let's see. Let the activations of the hidden units in the first hidden layer be given by this. So we have then z equals h of a. A is this linear combination of the weights, the inputs multiplied by the weights from the previous layer, and then there's a bias term as well, and verify that the network function is invariant under the transformation. So what is the transformation here? This is actually when you look at it, this is a affine transformation. It's not linear because if it were linear, it would be AXI. If you put also a constant, then it's called affine transform. All right. So what it tells you is, this is interesting. So affine transform, right? So if we apply an affine transform to the inputs, then provided the weights and biases are simultaneously transformed using these equations, then the network function is invariant. What does this mean? It's interesting. So if I take my inputs and pass them through an affine transform, and let's say these weights are determined by the training algorithm, then the training algorithm under the affine transform will still be giving me hopefully these transformed ones if it works well. So that means essentially affine transform of my data doesn't change the main result, because the network will find these transformed weights if the training algorithm works well, and then I will still get the same result. So it is kind of the neural network will be done robust with respect to this transform. How can we show that? This is kind of quite straightforward to show, because what we do is only thing we do is we can write the argument of h as zj equals h of, instead of this I write the transformed one and I put all the transform things into it. So I write it as sum over I. Let me write it first, ji tilde xi tilde plus j0 tilde, right? So if I write it this way, it would be then the sum over I. I would have done, this is simply 1 over a wji. Xi will be done axi plus b, and then plus the last one will be done, bias term will be done wj0 minus b over a, sum over wji. So this bias is the constant, so we get then rearrange the terms. If we rearrange the terms, a's cancel out, so I get then sum over wjixi plus b over a sum over I plus 0, I'm sorry, minus b over a. Then that actually obviously cancels out, so this cancels this, but then I get the same as the before, ixi plus 0. Notice this is actually a matrix multiplication, right? Because you are doing the columns, so you can actually write it as x. So that is a matrix multiplication, right? So yeah, that's it. There's nothing else in this question. So it's a simple fact that, you know, the linear transforms will not bother the neural network that much, as long as it finds these transformed weights. But then it's supposed to, you know, if you give the data set, it's supposed to find the correct ones. So let's go to this one. This is much more interesting, and then this would be probably the last question of the day, and then we will continue next week. So okay, this is kind of a good practice question, like a backpropagation question. So we have the two-layer neural network. Now I managed to put the neural network here. Actually, it's not two layers; it's a single hidden layer. But the second layer is the output layer, input layer, hidden layer, and the output. There's a single output here actually. This is the general picture. So there's a sigma, that's the activation function at the output, and we choose it to be identity. So actually it doesn't play any role. There is no sigma, in fact. It's just I put this expression as a general expression. So the initial input is passed through this linear multiplication, then the H nonlinearity, and then that's happening at the hidden layer, activation function at the hidden layer. Then those outputs, individual outputs, are again matrix multiplied with these weights. Another bias is added, and then you get the output. There's a single output in this case, right? And the question tells us now use the activation function tan-h, and then note that the derivative of tangent, hyperbolic tangent, is 1 minus ha square. So this is also very useful, because when you take the derivative, you just use the function itself. That's useful. And we use for convenience of the question, some square error function. So the question first asks, that is the good part, find the forward propagation equations. So that is important, because to be able to do the chain rule derivatives, you need to know what is going on with the function. So following the same notation as in Bishop, so we can actually write what are the forward equations. So the activation units are from I equals, so you see there's d, input dimension is d, and then there are maybe this is also something vert. So input d dimensional, right? Maybe I write it here first before I go. So input layer has d units, right? And then hidden layer has m units or nodes. Okay, that's comes from the sums immediately. So after noting that, we can actually write it in a generic way. So for a AJ, it would be then the sum of the combination of the inputs. If we ignore the bias terms, without actually they can be ignored or incorporated. So we get the first layer, right? Input to over the sum over I to get the AJ, and then once we have the AJ activation, we pass it through the activation function. Then ZJ will be then H of AJ. In this case, it will be then 10H AJ. And then now from these are the outputs of the hidden layer units. Then they need to be combined to get the input to the single to get the input to the single output. And because the activation function of the output is linear, the same thing, identity function, we don't need to write that. So we have just the J WKJ. Now they belong to the second layer, and let's write it a bit cleaner, and then ZJ, right? All right, because linear activation at output, and in this case we have a single output, therefore it's just one. There could be multiple outputs. The picture shows multiple outputs, but in this case we have a single output. Okay. So this is generic picture. Diagram. Not necessarily the correct one. All right. So this is these are what is called the feed forward propagation equations. Essentially, you write the input-output relationship function of your neural network in functional form in multiple pieces, but you can actually put them together like this. Write it as a long function, or you can write it in pieces. It's the same thing. Okay, so this must be clear to everyone, right? Because there's nothing mysterious here. So now the chain rule is actually also not difficult, it's just tedious. The right word is tedious. You need to be just careful taking those chain rule sums in a proper way. So now we will use actually the solution that we have derived as a generic solution. So remember, we have derived. It's kind of using like a cheat sheet. We have derived that the error at the jth one will be the derivative of that activation function with respect to AJ. So essentially, with respect to its argument. So let's make it a bit clearer. This is meant by that times sum over k, wkj, and del k. So this is the previous error is combined and then propagated, right? So now we compute. Now we find deltas for each output unit. So we have actually single one, but then that would be then delta k will be then yk minus tk, which is the correct label, right, for the kth one. Then we back propagate these to hidden. Back prop these or these to obtain deltas at hidden layer. So from output, you see, we go to the other direction, just like we did in the demo, right? At the hidden layer, then what would it be? Del J would be then, what is the derivative of tangent with respect to the A? It would be then 1 minus HA square, but that is Z, because the HA is Z from previous one. So it would be then ZJ squared. So that is this derivative. This is this. And then this sum will be here coming. It will be then sum over, yeah, we said K, let me put it that way, K equal the right size, J, and del K. So these are the errors at the delta, the deltas and errors at the hidden layer, at the input at the hidden layer. So then the derivatives with respect to the then with respect to the weights will be done using these. And the fact that, you know, what was it? The error gradient is the delta times the input. So therefore, del En with respect to del Wji in the first layer will be done simply del J times Xi, which is the input, right? So this is actually coming here, right? And then the other one, del En, del Wkj will be done with respect to, then they will be del K, which comes from here, right, times Zj, right? Yeah. So this is then C slides, but even more importantly, as I was saying in my email today, see also the respective chapter of the book, right? See slides and Bishop for, you know, a bit more detailed or more relaxed derivation that follows from this. And that demo also is really good when you want to visualize this. You can do it algebraically blindly, following the chain rule, but you can also, when you want the intuition, you can think of that demo that everything chain rule is actually going backwards. So that's why this is called the, you know, the question asks the derivatives, and this is the back propagation, because you start from the error and then go through the layers all the way to the input layer. Inputs, you don't take the derivative with respect to inputs. You want the derivatives with respect to, of course, you know, the weights, because we are going to use these derivatives in the updating the weights through the gradient algorithm. Right. Yeah. As I say, it's a Bishop relevant chapter. Yeah. The right way to use the slides. I mean, I'm trying to make them as detailed as possible. Whenever people ask me a question, I add an explanation. But the slides, by their definition, cannot be a handout, and they are not a book. So the issue is the books contain a lot of additional information. Then you might say to me, how am I going to read 3 chapters in one day? You can't. I know that. That's why you use the slides to go focus the specifics of that book. You know, the slide talks about something, you go to that subsection of that maybe book, where you have the same thing, but in a more detailed derivation, a bit more discussion. That is not reading the whole 3 chapters in one, you know, in 1 week. That is reading a little bit more than what the slides have, a bit more than what the slides have, and, you know, doing focused, you know, browsing and getting the information. So I think that is something we used to do. You know, when I was a student, we used to read the books. I don't know when things went wrong, but the current generation seems to be thinking always the slides are sufficient. They definitely are not. Actually, everyone hates these slides. I don't know why we are using, like, I was going to use whiteboard like this, but then it will take forever and you will have to suffer my bad handwriting. So I stuck with the slides. Initially, I had made that decision because everybody used to it. Whiteboard version would be badly written. You would be suffering. So I decided I still put slides, but I did it only as a necessary evil, to be honest with you, as a guide. Use it as a guide only, and then go to the book. If you cannot find it, let me know. I should put it actually underneath where it's coming from and so on. Like, I mean, specific even, I can put the page numbers into, you know, let me know. I can put that. So yeah, but read the books and do a bit of a back propagation reading. Once you understand it, there's nothing more to it. It's pretty straightforward as it sounds. It's just the chain rule, and you should be able to do that. If I don't ask it this year, I will ask it definitely next year in the final exam. The back propagation. It's something, you know, people should know about. We will continue next week, and then I will also post the slides for next week, hopefully by Friday. All right, thank you. And I'm late again.